Okay, thank you very much, Tilde, for chairing the session. And now we have our next keynote speaker, Krannich from Bremen University, who's just finishing his last slides. Dennis is a senior researcher at the work group of digital media in education, DMEP, and you might have seen them out in the demo area as well. He's an expert on digital media and digital fabrication in education, and he leads the Digital Experience Lab at the University of Bremen, and also is chairman of Fab Lab Bremen. They do very interesting work in Bremen, both with industries and with schools and also local communities. So they've actually tried many different things and been doing it for a long time, and they also have this Fab Lab at the university. So we're very pleased to have you here, Dennis, and to collaborate with you, and take it away.
Yeah, thank you very much for having me here, and thank you, Rachel, for this lovely introduction. And I would also like to thank all of you guys for creating and organizing such a wonderful conference. I think it's really great work, and I didn't expect so many people here that are interested in the topics that we do in research right now. So in my presentation, I'd like to pick up on the topic of our today's workshop that Paolo and I did before lunch, and I want to focus on HCI a little bit in detail. And as I promised in the workshop, I gathered the results and did a first analysis during the lunch break. By the way, if you want to take a look at these results, they are upstairs in the lobby, and you can have a look at them maybe after my talk. If you want to leave, feel free, but I don't know if I think it's kind of exciting what I want to talk about, at least for me. And I'm not sure if we can put them on the Fab Lab Europe website, Fab Learn Europe website. What I could figure out is that we discussed about two things: tools for digital fabrication. So questions were like, how can we improve education by using technology? How can we open the black box? What are possible tools to think with? And the second major topic we discussed today was implementing digital fabrication in schools, and I think that's what all the teachers are mostly interested in. So how to get digital fabrication into educational systems? This was one question. How can we create, can we get creativity in Fab Labs, and how to involve other teachers? So it's good that we have one small minority that is interested in Fab Labs, but we should get all the teachers. And yeah, this is what we talked about. And I want to focus right now on HCI a little bit more in detail, because we discussed the didactic part, I think, not enough, but in detail and just very thoroughly. So let's focus on the tools. And we, as an HCI practitioners, we design interfaces that make software easier to use. And honestly, this button would be great to have, but actually it doesn't exist. So just to give you an idea what we do in HCI, we are dealing with different disciplines like social sciences, psychology, and of course also computer science. And what can you expect from this talk? Hopefully I can give you, there's the animation. Hopefully I can give you some background information about Fab Labs in general, and then also some ideas for your own projects. And I will also I also want to invite controversy for discussion, hopefully in a good way. And I will leave you with some open questions for future research. And actually, I will raise more questions than giving answers. So I think in the discussion, maybe we can come up with some solutions. And we have a lot of solutions upstairs on our poster from our workshop. So check it out. This is a cartoon I recently received via email, and I really like it because of two things. So first, it's reflecting on the generations. And the second thing is that it also shows new possibilities that we now have with digital fabrication technologies. So they allow us to transform nearly any object from the virtual world, from the computer, into the physical world. And this transformation builds the basis of my today's talk. So before we dig deeper into the topic, I'd like to roughly summarize the rise of personal fabrication and explain a little bit what it is, and also conclude maybe first impacts. So the roots of this whole revolution in digital fabrication date back to the invention of the computer, obviously. So the ENIAC was the first general purpose computer that we have, and can be seen as the enabler of the first digital revolution. And since then, computers have changed the way we process data, and this is also very important for the second revolution, which happened in data transmission. So with the invention of the internet, we could send data from one place of the world to another and be connected with people over long distances. And both revolutions have one thing in common: they moved from analog to digital and changed the way we process, store and transmit our data. So digital data is recoverable, as we know. It's lossless, transferable, and cheap, and fast, and therefore ideally suited for reproduction and mass production. And this aspect started a similar shift from analog to digital in the field of fabrication. And this is where we're going now, towards fab labs. So analog fabrication became digital, and it was possible to digitally produce physical artifacts based on digital models. And digital fabrication is based on having a digital model of something you want to create, and then using a digital fabrication tool or machine to actually produce it. And now, due to the recent development in the DIY community, so here we see a 3D printer, digital fabrication becomes personal. So everybody can just go out to the shop and buy a 3D printer, put it on a desk, and become a creator. And this shift is kind of comparable to the one that has happened to computers in the early 80s. So who's from the early 80s? Who knows the computers in the early 80s? So welcome back to the future or to the past, whatever. So we are faced with the same problems, and we are nearly have to come up with a solution once again. And these developments led to the third digital revolution, a move from mass production to personal production and personal to design. So as I said, everybody can become a creator, which enables everyone to create the things they want by turning digital data into physical artifacts. And one major enabler are the so-called fab labs. And here you see the professor, Neil Gershenfeld from the MIT. He coined that term. And he says that, or he defines fab labs as an open environment that enables people to create almost anything. The idea was coined in 1998 when he started his class called How to Make Almost Anything. And then it started to spread in 2002 with first fab labs established in Costa Rica, India, Ghana, Norway, and the US. And the basic idea of such high-tech workshops, as they are also called, is that you come with an idea and you leave with a product. So you digitize your idea, you develop different prototypes, refining them in an iterative process, and finalize your product. And at the very end, and this is what is always left out, you share the knowledge, or you should share the knowledge you've gained within the Fab Lab community. And this process seems to be very easy, but honestly it isn't. And there are several obstacles we are faced with, and we will see later on what these obstacles are. And since the media is mostly focusing on 3D printing, when they're reporting about Fab Labs, I want you to notice that Fab Labs is more than that. So it consists of different machines like 3D printers, CNC mills, laser cutters, and vinyl plotters, enabling different manufacturing processes like additive manufacturing or subtractive manufacturing. And people are also dealing with microcontrollers and electronics to create interactive, computerized artifacts. As I said, one key aspect of Fab Labs is that they are embedded in a worldwide community to exchange knowledge. And right now there are over 340 registered Fab Labs on a website called FabLab.io and counting. And this number is actually quite higher because not all Fab Labs are registered on that website. So if you own a Fab Lab, please go to that website and register if you haven't done this already. Yeah, and today the Fab Lab community is considered to be a global knowledge sharing network spanning over 30 countries and 24 time zones. And in the last couple of years, the attention has increased tremendously, not only by the media, but also by politicians. Where is he? President Obama promoting Fab Labs and makers. And yeah, as we have seen today, also the politicians here in Denmark are very interested in this topic right now. So from the skyrocketing development, we can, I think, conclude two major things. First thing is that personal fabrication revolutionizes the way we design, develop, and purchase products tremendously. So we are moving from mass production away and replace this by on-demand production or self-made products. And some production companies will also have to change the business models from solely production to maybe services, like customizing or providing customizable objects, for instance. But this is a different story we don't want to talk about today. I'd like to talk about the second thing in more detail. So the second thing is that personal fabrication enables new accesses to learning. And we've heard that before. So here's the Trojan horse Paulo was referring to in the morning. Digital fabrication could be seen as a next Trojan horse to get kids interested in common theory, like mathematics, physics, and so on, and also 21st century skills. But also, as we pointed out in our workshop, this is just one tool. So personal fabrication is just one tool that we can use in school. So it's not revolutionizing everything. And this is, by the way, how a Trojan horse would look like if you create it out of paper. I found this online from a company called Autodesk. And in order to investigate this high potential, we firstly wanted to understand the objective of today's Fab Labs, how they are structured, how they are organized, and how they are used by visitors. So we've conducted an online survey from late September till mid-November last year, asking over 100 Fab Labs worldwide to take part. And I'd like to just roughly highlight the most interesting findings of that. So the first interesting aspect I'd like to point out is that 25%, actually we need this, 25% of the Fab Labs we've asked are situated in educational institutions. The others are either organized in independently, like in clubs, which is very famous in Germany, or maybe they say other, whatever this means. Maybe they are kind of companies, or we don't know. But yeah, the majority is not in the school, and I think this is also what we discussed in the workshop. Fab Labs do not necessarily need to be situated in schools. They can be in libraries that are accessible by pupils and also by normal citizens. So that we have open environments. And if you take a look at the area of interest, we can clearly identify the following 5 foci. So they're focusing on entrepreneurship, engineering, design, DIY, and also 74% of all Fab Labs focus on education. We will see in a minute what this means. And regarding the knowledge preservation and documentation, so I said that Fab Labs are situated in a worldwide network, or should be situated in a worldwide network. We can see that although 3/4 have installed special software for documenting the projects and preserving knowledge, this software is not used very regularly by all users in over 80% of all cases. So we have to come up with solutions for that, to encourage people to share their knowledge. And if we take a look at networking, we can see that all Fab Labs are interconnected via different channels, but only a few of them network on a regular basis. So this is also emphasizing that we also need to address this issue. But this is maybe also a different topic, and related to learning in general. From these results, we can, I think, conclude three main challenges for education. So the first challenge is that the majority is only interested in general education. So by means of exchanging knowledge or know-how and experiences. So what are your experiences with this 3D printer? I need to heat it, I don't know, to 240 degrees instead of 220 degrees. So this is what they want to exchange, know how to do some stuff, how to cut different materials. Only a few provide special offers for schools, and this is mostly rooted due to the structure. So their clubs they are opened only in the evening, and they don't have any full-time employees and so on. So only teachers who are club members actually use these facilities. I'm not talking about the facilities that are situated within schools or any university. So I'm talking about the independent organized Fab Labs. And second challenge is we can only integrate Fab Labs in school classes if we A, don't interfere or change the curriculum, because this is what is kind of fixed or rigid, and B, if we fit into the school's constraints. So a school lesson, at least in Germany, takes 45 minutes, or if it's a double lesson, 90 minutes, and it's hard to go to a Fab Lab that is located outside the schools. And it's also hard to do some projects within classes that last very long. And it's also very hard to get pupils encouraged in going to a Fab Lab. We just had in our workshop one participant reporting about a student saying, why should I go to a Fab Lab? What is it? What I learned there? Why should I go there? So what we do right now in our research is that we want to address these two issues. And we have a research project, it's called EduFab, and we try to come up with some educational material and see how we can situate the whole digital fabrication technologies within the schools. And one workshop that is currently going on, and this is our first workshop, is called Fab Around the Roland. And the Roland you can see behind the tram. It's a famous tourist attraction in Bremen, and the pupils rebuilt this place around the Roland, and they started with some drawings, as you can see in the second picture. Then they did some plasticine models from this place, and they cut out this first shape with a laser cutter, and this took quite a long time. But since this is work in progress, I don't have any concrete answers regarding didactics or learning material yet. But what I can say so far is that working with Fab Lab technologies in educational context does not require a commitment to a specific didactic approach, but is open to many forms and styles of learning and teaching. And it's also worth mentioning that a one-time visit or a one-day workshop is not sufficient for what we call in Germany Bildung. And therefore our approach does not aim to change existing or invent new didactic approaches, but to develop practically oriented and on Fab Lab technology closely related concepts that are compatible with different educational theories. And third thing, and this is what I like to concentrate on in the remaining time, is that we need to make this environment consisting of complex and machines and software accessible for the masses by providing a low floor, a high ceiling, and wide walls. So, as we have seen, we don't have to come up with solutions. We don't only have to come up with solutions on how to integrate Fab Labs into schools, but we also have to face different HCI-related issues in order to provide sufficient tools that are suited for learning. And when we create these artifacts with digital fabrication technologies, we always require the construction with a computer. And the first step is that we have an input. And this can be, as we have seen in the workshop example, a design drawing, a plasticine model, a 3D scanning, or we can also use digital data like GPS data or any measurements that you can or that we took from our sensors. And the second step, and this is what the results rely on, is the processing. And in this step, this input is transformed into a virtual object, into the computer, and the artifact can be modeled with a computer in 3D, or we can use 2D shapes to create our objects, but we can also use program environments. And with these program environments, we can, for instance, create 3D objects, 3D models, 2D shapes, we can also use digital data that is processed. And the last step is obviously the output, and depending on the artifact, we can transform the virtual model back into a physical object by using digital fabrication technologies. And when we are talking about this whole Bildungsthing, we know this whole German Bildungsthing or Allgemeinbildung, it is necessary to understand the whole process chain, and each of the required steps is and its corresponding tools. So the question is, how can we achieve this goal, and how does current software already support these demands? So according to Resnick, technology needs to provide us with a low floor, which is an easy way to get started, and a high ceiling, lots of possibilities for taking things even further. And there also needs to be wide walls that projects can be extended into other domains. And these demands from Resnick, I think, stand in direct relation to common patterns that we know from the HCI field. And when we're developing interfaces or software in general, we often see such things in HCI literature. And if we combine this to the Resnick, to the requirements by Resnick, we can say that beginners need an easy way to get started. So this is where we have the low floor, and experts need a lot of possibilities to take things even further. So we have a high ceiling. And as you can see, each target group has different questions, different needs. And in most cases, when we're developing software, we need to satisfy the perpetual intermediate, which is a very large target group in the middle. And designing software also involves two other things. So the systems implementation model, which is on the left side, and the user's mental model, which is here shown on the right side. And the implementation model describes the details of the way a program or a feature is implemented. And the goal of us HCI practitioners is to design what you can see in the middle, the represented model. So this is what the user actually sees, and this is what you see in your daily work with a computer. So this is the represented model. And the goal is to design this represented model as close as possible to the user's mental model. So if we combine this with Resnick demands, we can have a low floor and a high ceiling in two directions. So first, we can provide different functionality that reflects the user's mental model. And what this means is that we can have a low floor by just cutting out simple shapes, and they are engraved in a very simple way. And on the other side, we see a very complex object that has two different folding directions, so hill folds and valley folds. And here you can adjust the frequency and speed of the laser to create these. And an interface could maybe look like this. So this is an inspiration by a common dialogue. So you could have some settings for engraving, and you could also have some settings for cutting. And if you go a step further, you can define maybe different colors for your lines, and then have them cut differently. So this is what we could have as a high ceiling. And the other direction would be that we can go towards the implementation model, which is totally against any HCI related stuff. But in order to understand this whole black box, so we have a software that does some stuff and we don't understand what it actually does, we can open this and go towards the implementation model and open this for the user to understand what is happening within the software, to understand the whole process chain even better. And one example is a software we developed. It's called Amici, and some of you might go to the Tech Sportiv workshop. After this talk, they might see this software, and here we have a mental model, or the represented model, and we have the implementation model side by side. So you can arrange the different pieces and see how the program actually builds up, and how the program is changing by dragging and dropping different pieces onto it. And the other way around, it would also be great if we could change the code and see how the mental model on the other side is changing. And if we take a look at the challenges users are faced with in Fab Labs today, we see a strong demand for new and more suitable tools that support this low floor, high ceiling, and wide walls. And they are faced with lots of challenges, and I'd like to highlight 3 of them in the remaining 5 minutes. So the first thing is that people are unable to construct artifacts on their own. So it's not possible for them. So here you see a professional design software, which is called SolidWorks. And for instance, if you want to rotate an object, you need to know the concept of a rotation axis first. And such concepts are not suited for ordinary users. And also I have some problems with this. Google SketchUp was originally intended to enhance Google's map service with user-generated content. And since it's easy to use and easy to understand, people use it to construct normal artifacts, and even kids use this tool to in our workshops, and they can create simple objects. However, the entry level remains high if you want to construct complex objects. Autodesk, on the other side, tries to come up with a different solution. They want to enter the new market with different applications under the label of 123D. And there's a design program, for instance, with which you can create these objects here out of simple shapes. There's 123D Catch, so you can take a picture of an object with your iPhone, for instance, and then you have a 3D model. There's 123D Make, and you can just print it out, this 3D object, by 2D slices. If you want to create complex objects also with this software, it's not possible. So we definitely need these types of professional design tools, yes, but what we need for beginners are simple tools. And here you see an example that is just suited for one purpose. It creates a box. And you can define the dimensions, you define the thickness of your material, and then you get a box. You can, not with this software, but with a similar software, you can also create these banded shapes, for instance. Another example would be SketchChair by Greg Saul, which allows you to create chairs. And they've also implemented a kinetic engine to simulate how a person would actually sit on the chair you have created. And either the person sits or falls off the chair, so you can test before you produce your actual object if this works in reality or not. If you want to create 3D objects out of 2D shapes, you can use Flattery, for instance. This is a plugin for Google SketchUp that transforms and unfolds 3D objects into 2D shapes. So we need to understand the construction tools, and we need easy to use and easy to understand construction tools. And another issue is that people are not able to operate these machines. So here we see an example of one software where you can specify very precisely how to print out your object with a 3D printer layer by layer, and you can specify the parameters of each layer. Cura, which is a software by Ultimaker, came up with a different solution. For beginners and experts, you can switch the modes and specify what you want to do. Here again, this printer dialog, we have seen this before, but I highlighted the things I have changed. So who knows what raster settings are or vector settings are? The mental model is engraving or cutting. So this is what we should keep in mind. RWTH Aachen, a German university, came up with VisiCut. So you can select first the tool that you're using, then you specify the material, and then you can cut out the whatever shape you have with your laser cutter. But still, this isn't suited for all people. I will skip this because of lack of time, I'm sorry. But we also need to address the hardware issues. So in conclusion, we need intelligent and customizable user interfaces to suit different user goals and contexts. And the third challenge is very essential, and now we come back to the beginning of my talk, to enrich the worldwide Fab Lab community and to fulfill also Gershenfeld's initial intention of sharing knowledge. So most projects are done independently, nobody knows about it, and the know-how remains hidden. So we have tools like Instructables or Thingiverse. I'm glad that Paulo is developing Constructables, and guess what? We are also doing a similar project. It's called Transportal. This is just one of ours. So this is in beta stadium. And we also want our visitors in the Fab Lab to document their work and their steps they do and share the knowledge and the experiences with others. So in conclusion, we need appropriate collaboration and sharing tools. And this leads me to the end. So you can see that there are lots of opportunities and challenges we have to tackle, also in the field of HCI, not only in the field of didactics. And we are just at the beginning. So that's it. I'm open for questions now.
Thank you very much, Dennis. I already see some hands going up.
Thank you for a very interesting speech. You said at one of the points that it had to be within the curriculum, but what Paulo said was that we have to make space for it. We have to select that we want to do this, and then we have to get rid of something else. So maybe we have to make space for it, or else it will just be another thing to put on top. In Germany it might be a little bit different than maybe in the US, but I totally agree with Paulo's idea of that we need to make space for it. And in German education system, you cannot just say, okay, we need to make space. So this is maybe the second step. The first step is first we need to integrate it in the curriculum, which we try with our workshop Fab Around the Roland. So that we can teach children with our Trojan horse mathematics. And they do a lot of mathematics without knowing it. And they do a lot of different other things without knowing it. Also the 21st century skills, they will learn it there, so all the soft skills. And this might be maybe the first step, at least for Germany. And then we can go in and say, okay, this works, and now in order to be even better, we need to change it. It's just one idea that we have, and all the teachers in Germany, they say, yeah, it's a good thing, but how can I do it? I just have 90 minutes time, and I need to go to the Fab Lab, and this takes time, and so it's hard to achieve, at least right now, as it is right now.
Hi. Yeah, I think I'm sitting here thinking about cardboard because I used to be a maths teacher, and I used to spend a lot of time having children build nets of models so that they could then stick them together and end up with big shapes. And I'm sort of thinking about 3D thinking, and I'm wondering if you have any thoughts on this as to whether children are less good at 3D thinking because of our 2D interfaces. And about 4 slides back you showed a picture of some piece of software where you could draw something and the software would fold it up. It's nothing like as tangible as actually having it on a piece of paper. So I'm kind of wondering if we might be in some sort of strange space where children can't think 3D. And
Yeah.
I'm not convinced that putting it all on a screen and then printing it all out will actually change that. So just your thoughts really, yeah.
Yeah, so this maybe just some tools that you can use to say, okay, if you have a 3D object, you can unfold it with a software plugin. But what we also want is that the pupils understand what is going on in this black box and how this works. And for this, you have to open the black box and see how this actually works and explain how maybe the algorithms work behind this to unfold these objects. And we don't give them a 3D model or let them create a 3D model and have it cut it out with this plugin. At first we say, okay, now you create it yourself, and you have to understand how to do it, how to unfold these objects, and get an idea how to project these 3D objects into a 2D, into the flat world that we know, and then we can use the tools to support it. So I think it's a whole discussion like with a calculator all over again. So people were afraid that pupils are not able to calculate anymore. If you go into school classes, I would say yes, it got worse. They need to use the calculator more often than maybe we did it or you did it. Some are a bit older than me. But I think it's important to understand how to solve real world problems, and therefore we have new tools that we can use. So does this answer your question a little bit? Just a little bit, okay, yeah. Okay. And don't forget to check out our poster.
So Dennis, I was just interested in, you were talking about having like flexible and customizable interfaces that sort of adapt to the user actually using it and the level of expertise they have. So do you have, you mentioned the Arduino / virtual sort of sketcher thing going on there. There are, what did you call it? Amici, yeah. Do you have any other examples of like a software that sort of determines your skill levels and based on that sort of customizes the interface?
Like, yeah, as I've shown, this Cura software by Ultimaker, they can just also change the user interface to a professional mode, and I think lots of programs can do it right now. But what they don't do, and this is what might be interesting, and it might also be a good research project, is to create a similar approach like Amici for 3D objects. So how are 3D objects created? We have this software called OpenSCAD. Do you know OpenSCAD? Who knows OpenSCAD? One. So this allows you to create 3D objects by programming simple shapes and then applying different modifications. And if we can combine these concepts with this, what we did in Amici, that you have a 3D object and then you click on it and then you see the corresponding code and vice versa. So that would be great. But right now we don't have it.
I'm thinking more like if it could actually change the interface automatically, so the user doesn't like have to make the choice like I'm a professional, I'm an expert, I'm a newbie, you sort of have to make that decision yourself, or you have to have something
so
else
the software takes care of changing the user interface
sort of
according to your experiences.
Yeah, exactly.
And well, it's also a good idea, yes. But let's start easy. So, yeah.
Okay, thank you, Dennis.
Thank you very much.
Just one last question.
Yes.
You talk about things that are going on on the developing side of things. I mean, how do you develop programs and how do you develop different environments to do learning with digital fabrication? which is a different type of discussion than goes on in the schools, where they say, I have to teach these kids a certain topic. How do I actually draw in digital fabrication technologies in this context? So, for all the teachers here, what would your suggestion be, or your best piece of advice?
Yeah, it's a good question. Convince politicians to create more fab labs, so, and maybe also in the schools, so that you have short ways to go there. Maybe so this is what our biggest problem is, and then we should come up with ideas how to create these real world problems and then fit it into school context once again, and apply common theory.
So going through, taking the subjects of the teaching and then applying real world problems through the use of technology.
I would go vice versa, or the other way around, starting with a real world problem and see how I can apply this in schools, and if it's not suited in math, maybe it's suited in physics or something like this. So I think it's not very satisfying for the teachers here in the room to go this way, because you all have your problems like, oh, how do I teach in physics? I don't know, some certain phenomena. So yeah, it's.
So we need to revise the teaching.
Yeah, first the idea, and first show, like Paulo said, first do it and then show how. Do it and then show how it works. Yeah.
Yeah. Okay. Thank you very much, Dennis.
Yeah.
So now we have coffee and last workshop sessions, and I hope you're all ready to go. And I hope we'll see you all back here for some drinks and some food after the session.